Most locomotives are built to do a job. A small number are built to push engineering as far as it can possibly go. Locomotives so large they could not fit on existing track. So powerful they ripped themselves apart. So strange they had no equivalent anywhere else in the world. These are the machines that defined the upper limits of what a locomotive can be. Some of them succeeded. Some of them failed catastrophically. All of them represent the moment when railroad engineers asked the question, how far can we push this? We are counting down from 10 to 1. The list will surprise you. The number 1 entry will start arguments. Let us begin. Every era of railroad history has produced locomotives that pushed beyond the conventional. The reasons varied. Sometimes the existing technology had failed to meet operational demands. Sometimes, a single railroad had a problem so unique that no standard locomotive could solve it. Sometimes engineers simply wanted to see what was possible. An extreme locomotive is not just a large locomotive. It is a machine that violates the assumptions other locomotives are built around. Different drivetrain, different layout, different fuel, different operating philosophy. Some of the entries on this list pushed steam technology to its absolute limit. Some pushed diesel-electric power to its theoretical maximum. Some abandoned conventional technology entirely in favor of approaches nobody else had tried. Every entry was extreme for a reason. Some of those reasons turned out to be wrong. The wrongness is what makes the story worth telling. Number 10. The American Locomotive Company PA, the most beautiful diesel locomotive ever built, and one of the most extreme failures in American railroad history. The PA was introduced in 1946 as ALCo's answer to EMD's dominance of the post-war passenger diesel market. 2,000 horsepower from a single 16-cylinder prime mover, streamlined cab unit design, deep, distinctive exhaust note that earned it the nickname Honorary Steam Locomotive among rail enthusiasts. Visually, the PA was extreme, the longest cab unit ever built, sweeping streamlined lines, a presence on the rails that EMD's more conservative designs could not match. Railroads ordered them to lead their flagship trains specifically because the PA looked like the future. The extreme part was the engine. The ALCo 244 prime mover was rushed into production with mechanical problems that were never fully resolved. Cracked cylinder heads, cooling system failures, endemic reliability issues that meant a PA spent more time in the shop than its EMD competitors did in service. 297 PAs were built between 1946 and 1950. Most were retired within 15 years. Barely half the service life of comparable EMD units. The class was effectively extinct in American service by the late 1960s. The PA is on this list because it represents an extreme failure of execution. The design was extreme. The ambition was extreme. The reliability was so far below industry standards that the machine destroyed ALCo's competitive position in the diesel-electric market. Within 20 years of the PA's introduction, ALCo was out of the locomotive business entirely. Number 9. The Krauss-Maffei ML-4000, a German hydraulic transmission diesel locomotive imported by 3 American railroads in the 1960s. The most extreme example of failed technology transfer in railroad history. Conventional diesel-electric locomotives use the diesel engine to spin a generator, which produces electricity, which feeds traction motors that turn the wheels. The ML4000 did something fundamentally different. It used a hydraulic torque converter to transmit power directly from the diesel engine to the wheels. No generator, no traction motors, no electrical drivetrain at all. The German railway system had been using diesel hydraulic locomotives successfully for years. The technology was mature, the performance was excellent. Krauss-Maffei was confident it would translate to American operating conditions. 3 American railroads bought the ML4000. Southern Pacific, Denver, and Rio Grande Western, the Erie. They wanted 4,000 horsepower in a single unit at a time when the most powerful American diesel-electric was producing 2,400. The trial was a disaster. The hydraulic transmission could not tolerate the dust, the temperature extremes, or the duty cycle of American freight service. Maintenance was complex. Replacement parts had to come from Germany. The shops did not have the expertise. The reliability collapsed. All 37 ML4000s built for American service were retired by the early 1970s. Most went straight to scrap. The hydraulic drive experiment ended American railroading's flirtation with non-electric transmission for the next half-century. The ML4000 is extreme because it tried to import an entire alternate technology paradigm into a market that had standardized around something fundamentally different. The German locomotives were not bad machines. They were the wrong machines for the country they were sold into. Number 8. The Erie Triplex. The most extreme articulated steam locomotive ever built. A machine with 3 complete sets of drive wheels and a design philosophy that pushed steam technology past its useful limit. A standard articulated steam locomotive has 2 engines, 2 sets of cylinders, 2 sets of drive wheels, under a single boiler. The triplex had 2 engines under the boiler arranged conventionally, a 3rd engine under the tender. The 3rd engine was the extreme element. By placing a powered engine under the tender, the triplex could apply tractive force across 3 full driver sets, 24 total drive wheels. The starting tractive effort was theoretically the highest of any steam locomotive in the world. 3 triplexes were built by Baldwin in 1914. The Erie Railroad bought them for use as helper engines on the steepest grades of its main line. The starting tractive effort was real. The triplex could lift heavy freight trains over grades that conventional articulated locomotives could not handle alone. But the triplex had a thermodynamic problem that no engineering refinement could solve. The boiler could not generate enough steam to feed 3 engines simultaneously at speed. The triplex worked at very low speeds, where steam demand was modest. As speed increased, steam pressure dropped. Performance collapsed. All 3 triplexes were rebuilt back into conventional articulated locomotives within 15 years. The 3rd engine set was removed, and the tender was rebuilt as a conventional non-powered tender. The experiment was over. The triplex is extreme because it pushed the articulated steam principle 1 step too far. 2 engines on a single boiler, the basic articulated design, works. 3 engines on a single boiler does not. The Erie Triplex demonstrated the limit by exceeding it. Number 7. The Pennsylvania Railroad Q2. The most powerful non-articulated steam locomotive ever built in America. 6,000 indicated horsepower from a single rigid frame. And one of the most extreme expressions of an engineering philosophy that did not work. The Q2 was a duplex locomotive, a design with 4 cylinders driving 2 separate sets of drive wheels on a single rigid frame. The configuration was 4-4-6-4, 8 pilot wheels, 8 drivers in a 4-6 arrangement, 4 trailing wheels. The Pennsylvania Railroad believed that articulation introduced unacceptable tracking instability at high speeds. Their solution was the duplex. Multiple driver sets, but all on a single non-articulated frame. The Q2 was the ultimate expression of this philosophy applied to freight service. 25 Q2s were built between 1944 and 1945. They were extraordinarily powerful in laboratory testing. In actual service, they revealed every weakness of the duplex concept. The 4-cylinder design had endemic wheel slip problems on starting. Without articulation, the long, rigid wheelbase punished track at every curve. The mechanical complexity made maintenance brutally expensive. The Q2 used more steam per ton-mile than the conventional articulated locomotives it was supposed to replace. All 25 Q2s were retired within 10 years of construction. The class was scrapped completely by 1954. Not one survived into preservation. The Q2 is extreme because it represented the absolute theoretical maximum of steam horsepower in a non-articulated locomotive. The Pennsylvania Railroad spent enormous engineering resources proving that the maximum was not high enough. The articulated locomotives the duplex was designed to replace continued operating into the late 1950s. The Q2 was extinct before the technology it competed against. Number 6. The Baldwin Centipede, an extreme diesel-electric design that helped destroy one of America's largest locomotive manufacturers. The Centipede was Baldwin's attempt to compete with EMD and ALCo in the post-war diesel market. 3,000 horsepower per unit, distinctive 24-wheel layout, 8 powered axles plus 4 pilot axles at each end. Streamlined carbody, built between 1945 and 1948. The wheel arrangement was extreme. Most diesel locomotives of the era had 6 powered axles total. The Centipede had 8, distributed across an unusually long carbody. The design was supposed to deliver dual service capability, passenger speeds with freight horsepower. The execution was a disaster. Baldwin's diesel engines had reliability problems that approached the ALCo 244s. The complicated wheel arrangement multiplied the maintenance burden. The dual service flexibility was theoretical. In practice, the Centipede was bad at passenger service and worse at freight. Pennsylvania Railroad and National Railroads of Mexico were the primary buyers. Pennsylvania retired theirs by the late 1950s. Mexico operated theirs into the 1970s as low-priority switchers. None survive. Baldwin's locomotive division was effectively dead by 1956. The company that had built more than 70,000 steam locomotives over a century could not transition successfully to diesel-electric power. The Centipede was not the only reason, but it was emblematic of every reason. The Centipede is extreme because it tried to solve too many problems at once: long-distance passenger service, heavy freight, dual-service flexibility, mechanical innovation, aesthetic ambition. The locomotive that tries to do everything usually does nothing well. The Centipede demonstrated that lesson at a scale that destroyed its manufacturer. Number 5. The EMD SD90MAC-H, the most powerful conventional diesel-electric locomotive ever built. 6,000 horsepower from a single unit. And one of the most extreme failures in modern American railroading. EMD introduced the SD90MAC-H in 1996 to compete with General Electric's AC6000CW. Both manufacturers were responding to a railroad industry demand for higher single-unit horsepower. Railroads wanted to reduce locomotive counts on heavy freight trains by deploying more powerful individual units. The H-engine prime mover was the extreme element. EMD developed an entirely new 16-cylinder design, the 265HI, to deliver 6,000 horsepower in a single unit. The engine was larger, heavier, and more thermally aggressive than any previous EMD prime mover. The reliability problem started almost immediately. The 265H engine experienced repeated failures in service, cracked cylinder heads, cooling system inadequacy, vibration issues that propagated through the locomotive structure. Railroads that had invested heavily in the SD90MAC-H found themselves running locomotives that spent more time in the shop than on the road. Union Pacific eventually rebuilt nearly its entire SD90MAC-H fleet, replacing the failed H engines with conventional 710 series prime movers and downgrading the locomotives to 4,300 horsepower. The H version was effectively extinct by the early 2000s. The SD90MAC-H is extreme because it represents the moment when the modern American locomotive industry hit a wall. 6,000 horsepower from a single unit was theoretically achievable. In actual service, the reliability cost outweighed the power benefit. American railroads have not pursued single-unit horsepower at that level since. The General Electric AC6000CW had similar reliability problems. Both manufacturers retreated from the 6,000 horsepower goal within a decade. The SD90MAC-H is the more extreme story because EMD invested more in the failed prime mover and absorbed more of the financial damage. Number 4. The South African Railways GL-class Beyer-Garratt, the largest Garratt locomotive ever built. The most extreme expression of articulated steam technology applied to narrow-gauge railroading. The Garratt principle was developed by British engineer Herbert William Garratt in the early 1900s. A single boiler is mounted on a center frame. 2 complete engine units, wheels, cylinders, valve gear, articulate from the front and rear of the boiler frame. The result is an articulated locomotive with extreme curve handling capability and longer effective boiler length than rigid frame designs allow. The GL class was operated on South African Railways 3-foot 6-inch gauge, narrower than American or European standard gauge by nearly 2 feet. Extreme power on narrow track was the design challenge. Beyer Peacock in Manchester delivered 8 units between 1929 and 1930. The GL was extreme on every measurable dimension. 89 feet long, 222 tons fully loaded, tractive effort that exceeded most full-gauge American locomotives, all operated on narrow-gauge track that would have been considered inadequate for a fraction of the GL's weight in any other rail system. The GLs operated successfully for decades on the South African coal lines they were built for. Their performance vindicated the Garratt concept at the absolute upper limit of what the design could achieve. They demonstrated that articulated narrow-gauge steam could match and exceed standard-gauge performance. A demonstration that no other rail system replicated. The GLs were retired in the 1970s as South African railways transitioned to diesel and electric power. None survived in operating condition. The Garratt design itself effectively ended with them. No Garratts of comparable size were ever built again, and the world's narrow-gauge railroads have not produced anything close to the GL's power-to-track-weight ratio in the half-century since. The GL class is extreme because it represents the maximum theoretical limit of an entire locomotive design philosophy. The Garratt principle was pushed as far as engineering and metallurgy of the 1920s allowed. The result was beautiful, functional, and quietly dominant in its specific operating environment. American rail enthusiasts who have never heard of the GL class are missing one of the great success stories of extreme locomotive engineering. Number 3. The Pennsylvania Railroad S1, the largest non-articulated rigid-frame steam locomotive ever constructed. The most extreme expression of duplex design philosophy ever attempted, and a machine that was effectively obsolete the day it entered service. The S1 was unveiled at the 1939 New York World's Fair as the Pennsylvania Railroad's vision of the future of steam. 6 pilot wheels, 4-4 duplex driver arrangement, 6 trailing wheels, 140 feet long fully assembled, 6,500 horsepower at speed. The streamlined bodywork by Raymond Loewy made the S1 the most photographed locomotive of its era. The visual impact was unprecedented. American railroad engineering had produced something that looked like industrial design from a different decade. The extreme part was the operational reality. The S1 was so large that it could not negotiate most of the Pennsylvania Railroad's actual curves. Service operation was restricted to the Fort Wayne to Crestline section in Ohio, the longest stretch of straight track on the entire Pennsylvania system. Anywhere else, the S1 derailed. At speeds the operating department considered routine for normal locomotives. One unit was built, number 6100. It operated for approximately 8 years before being retired. The class was scrapped without ceremony in 1949. No surviving examples. The S1 is extreme because it pursued maximum size and maximum power at the cost of basic operational compatibility. It could not negotiate the curves of its own railroad. It existed almost entirely as a publicity vehicle for a railroad that had decided steam locomotives needed to be larger than their infrastructure could accommodate. The S1 proved that engineering ambition can produce a machine that succeeds aesthetically and fails operationally on the same delivery date. The smaller, more practical successor that followed the S1 was the basis of every most beautiful steam locomotive list that has been published since. The S1 itself is extreme. Its successor was usable. That distinction defines the entire post-war steam locomotive design crisis. Number 2. The Union Pacific Big Blow, the most powerful single-unit locomotive ever operated in regular American revenue service. 8,500 horsepower from a gas turbine drivetrain. The Big Blow was the second generation of Union Pacific's gas turbine electric experiment. The first generation arrived in 1952, 10 units producing 4,500 horsepower each. The second generation, introduced in 1954, doubled the output. 15 units were built, each generating 8,500 horsepower. A third generation followed, 30 more units with distinctive covered walkways that earned the public nickname veranda turbines. The drivetrain was extreme. Union Pacific had taken industrial gas turbine technology, the same technology used in jet aircraft and stationary power plants, and applied it to a locomotive. The turbine spun a generator. The generator fed traction motors. The output exceeded the most powerful diesel locomotives of the era by a factor of 3. Sherman Hill, the highest point on the Transcontinental Railroad, was the operational target. A single Big Blow could haul freight that previously required multiple diesel consists. On the actual grade, the turbine performance was extraordinary. The extreme part was the operating economics. Gas turbines are highly efficient at full power and dramatically inefficient at partial loads. The Big Blow burned ruinous quantities of bunker C residual fuel oil at the partial load operations that represent most of actual railroad work. The blades of the turbine itself were eroded continuously by contaminants in the bunker C fuel. Union Pacific operated 55 gas turbine locomotives over 17 years. By 1969, the entire fleet had been retired. The combination of fuel cost, blade erosion, and the arrival of more efficient 3,000 horsepower diesel-electric units made the gas turbine economically untenable. One unit survives. Number 18, preserved at the Illinois Railway Museum. Static display only. The most powerful single-unit locomotive type in American history is reduced to a single non-operational example. The Big Blow is extreme because it operated at a power level that no conventional locomotive design has matched in the half-century since. The gas turbine experiment proved that single-unit horsepower could be pushed past 8,000. It also proved that pushing it that far was not economically sustainable. American railroading has spent the last 50 years operating at horsepower levels far below what the Big Blow demonstrated was technically achievable. Number 1. The Union Pacific Big Boy. The largest and heaviest steam locomotive ever built and operated in regular revenue service. 7,000 horsepower, 1,200,000 pounds, 132 feet long. The most extreme locomotive that ever actually worked. 25 Big Boys were built by ALCo between 1941 and 1944. The mission was specific: move full wartime freight consist over the Wasatch Mountains of Utah without helper engines. The mountains were strangling the American war effort. The Big Boy was the response. The 4884 wheel arrangement was the largest articulated configuration ever applied to a successful production locomotive. 2 sets of 8 drivers each, 2 cylinder sets, a boiler producing steam at 255 pounds per square inch. Tractive effort that exceeded any previous American steam design by a meaningful margin. Unlike most entries on this list, the Big Boy succeeded. 25 units were built. All 25 operated successfully for the entire steam era. They moved the steel and oil and grain and ammunition that fed the war machine. They did the job they were designed to do. The Big Boys retired between 1959 and 1962. 8 units survived into preservation. 17 were scrapped. The class became static museum pieces, beautiful, important, finished, and then in 2013, Union Pacific retrieved number 4014 from a California park where it had sat outdoors for 54 years. They rebuilt it from the frame up. In May 2019, after 6 years of restoration work, 4014 moved under its own power for the first time since 1961. Today, Big Boy 4014 continues to operate on Union Pacific mainline service. It is the largest steam locomotive currently operating anywhere on Earth. The most extreme locomotive ever built is also one of the few extreme locomotives still running. The Big Boy is the number 1 entry on this list because it represents the rarest combination in extreme locomotive engineering: maximum size, maximum power, and operational success. Most of the locomotives on this list pushed engineering past the point of usefulness. The Big Boy pushed engineering exactly to the limit of what was useful, and stopped there. The Big Boy is the answer to the question every entry on this list was asking: how far can we push this? The Big Boy represents the answer that actually worked. Every other locomotive on this list represents an answer that did not. Ten extreme locomotives. 10 different definitions of extreme. Some of them succeeded. Most of them failed. All of them represent the moment when railroad engineers asked how far a particular technology could be pushed, and got an answer. The ALCo PA was extreme in execution failure. The Krauss-Maffei was extreme in technology mismatch. The Erie Triplex was extreme in mechanical principle. The Q2 was extreme in design philosophy. The Centipede was extreme in commercial damage. The SD90MAC-H was extreme in modern reliability collapse. The Beyer-Garratt GL was extreme in narrow gauge scaling. The S1 was extreme in operational impracticality. The Big Blow was extreme in raw power. The Big Boy was extreme and successful. What unifies this list is not size, power, or technology. It is the willingness of railroad engineers to push past the conventional and discover where the limit actually was. Sometimes the limit was higher than they thought. Most of the time it was lower. The locomotives that succeeded after these failures benefited from the lessons. The diesel-electric design philosophy that dominates modern railroading was shaped as much by the Centipede's failure as by EMD's success. The articulated steam designs that worked in the late steam era were shaped by what the Erie Triplex demonstrated could not work. The comment section is going to disagree about the rankings. The comment section is going to argue about the inclusions. The comment section is going to call for the locomotives we did not include: the Aerotrain, the Schienen Zeppelin, the GEU 50, the Pennsylvania T1, the Krauss-Maffei ML4000, the Soviet experimental classes. Tell us what we got wrong. Tell us your top 10. The whole point of this list is to get the conversation about extreme locomotive engineering started. There are more machines that deserve a defense than any single video can provide. 10 extreme locomotives. 10 lessons in engineering ambition. The most extreme locomotive ever built is, in our opinion, the Union Pacific Big Boy, because it pushed every metric to its limit and survived the experiment. Most of the others on this list did not. Drop your top 10 in the comments. Tell us which entries we got wrong. Tell us which extreme locomotives we should have included. Tell us which rankings are indefensible. Subscribe if you want to argue about more locomotives. There are more lists coming. There are more extreme machines that deserve their own deep dive. And there are more engineering experiments hidden in railroad history than most viewers will ever encounter anywhere else.